Hello there, and welcome to the Quiet Universe. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do now but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened. Because tonight, we aren't simply stargazing. We're drifting through the vast wonders of the universe, exploring its mysteries gently, one by one. You'll hear about distant galaxies and friendly stars, about things that puzzle scientists and sights that spark our awe. Some of what you hear tonight may surprise you, or at the very least, spark a quiet curiosity as you drift off to sleep. And just before we begin, if these calm cosmic explorations help you unwind and give you a soothing way to end your day, consider liking and subscribing to our channel. It helps other sleepy souls discover these journeys too, one starry night at a time. Now let's begin. The observable universe is unimaginably vast, containing perhaps 2 trillion galaxies, each with billions of stars. From our tiny world, we gaze out at an expanse so large it stretches the limits of our imagination. There are more stars in the cosmos than there are grains of sand on all the beaches on Earth combined. Every point of light in the night sky is just one grain in an endless cosmic desert. And beyond the stars we see, countless more shine unseen in the darkness. When you look into the night sky, you are seeing ancient history. The starlight reaching your eyes from distant stars set out long before you were born. From some stars, it began its journey before humans even existed. In this way, telescopes are like time machines, peering into the deep past of the universe. The Milky Way, our home galaxy, is a broad river of starlight arching across the sky. It contains hundreds of billions of stars, yet it's just one galaxy among the trillions in the cosmos. We live tucked away in a quiet corner of this vast spiral, a little neighborhood in a vast cosmic ocean. At the center of the Milky Way lies a supermassive black hole, about 4 million times the mass of our Sun. It's named Sagittarius A star, pronounced A star. Though we cannot see this black hole directly, it's a silent, dark heart. We know it's there by the way its intense gravity makes nearby stars whirl around it at astonishing speeds. Those stars orbit an invisible point, whipping around as if tugged by a massive but unseen hand. Black holes are regions where gravity is so intense that nothing, not even light, can escape once it falls in. They are like bottomless wells in the fabric of space and time. What lies inside, at the very center, the mysterious singularity, is unknown. It's a place where our current laws of physics break down. A black hole's boundary, the event horizon, is a one-way door in the universe. Things can fall in, but nothing comes back out. We have actually seen evidence of a black hole, or rather, its shadow. Using radio telescopes spanning the globe, scientists recently imaged the surroundings of the black hole at the core of a distant galaxy called M87. The result was a fuzzy, ring-like glow, light from hot gas encircling a dark center where the black hole resides. It was humanity's first direct glimpse of one of these cosmic enigmas, confirming that black holes are not just theory or science fiction, but real. If you fell into a black hole, gravity would stretch and squeeze you terribly, a process sometimes nicknamed spaghettification. Time would slow dramatically for you relative to the outside world. To a distant observer, you would never quite appear to fall in. You'd seem to freeze and fade near the black hole's edge. It's a mind-bending thought experiment that shows how bizarre gravity can be. When 2 black holes collide and merge together, they don't produce a flash of light that we can see with telescopes. Instead, they send ripples through space itself, gravitational waves. These waves spread out like the ripples on a pond after a stone is thrown, except they are ripples in space-time. In 2015, scientists detected such waves on Earth for the very first time, confirming a prediction Albert Einstein had made 100 years earlier. Two black holes over 1 billion light-years away had spiraled into each other, and the fabric of space quivered from that collision, ever so slightly, by the time it reached us. Gravitational waves are extremely faint by the time they wash over us. The signals detected were stretching and squeezing distances by a tiny fraction, much smaller than an atom. And yet, from that whisper-like signal, we learned about a titanic collision in the depths of space. We heard two black holes merging in a far-off galaxy by listening to the universe in a whole new way. Neutron stars are another extraordinary marvel of the cosmos. These are the collapsed cores of massive stars that exploded as supernovas. A neutron star packs more mass than our Sun into a sphere only about 20 kilometers, 12 miles, across, roughly the size of a city. They are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. Imagine a mountain crushed into a spoon. That's the kind of density we're talking about. Some neutron stars spin incredibly fast, hundreds of times per second. As they spin, they shoot out beams of radio waves and sometimes X-rays from their magnetic poles. If those beams sweep past Earth, we detect pulses of radiation, like a lighthouse beacon blinking in the darkness. We call these rapidly spinning neutron stars pulsars. The first pulsars puzzled astronomers greatly. The signals were so regular, like clockwork, that some scientists half-jokingly labeled them LGM for little green men, wondering if they might be alien beacons. We now know they are natural cosmic lighthouses, the spinning remnants of stars. One particular pulsar lies at the heart of the Crab Nebula, the beautiful expanding cloud of a supernova that was observed by Chinese astronomers in the year 1054. That pulsar spins about 30 times a second. Each flash we detect is a reminder of a star's death long ago, and the strange, tiny stellar corpse left behind, flashing forever in the darkness. Magnetars are a special, even more extreme type of neutron star. They have magnetic fields trillions of times stronger than Earth's magnetic field, the most magnetic objects known in the universe. A magnetar's field is so intense that if one were magically brought within a few 100,000 kilometers of Earth, it could erase every credit card on the planet and even disrupt the bioelectric processes of our bodies. Magnetars occasionally quake. Their strong fields can stress and crack their crusts. And when that happens, they emit bursts of high-energy radiation, like gamma rays. We've detected such bursts from thousands of light-years away. These are starquakes on a dead, dense star, and they remind us how violent and strange the universe can be, even in objects only a few miles across. Not all stars end their lives quietly. The most massive ones die as supernovae, colossal explosions that briefly outshine entire galaxies. When a star much bigger than our Sun runs out of fuel in its core, it can no longer hold itself up against gravity. The core collapses suddenly, and the infalling outer layers rebound in a huge blast. In those final moments, the dying star forges heavy elements, gold, silver, uranium, and others, and flings them out into space. Every element in your body heavier than iron, like the iodine in your thyroid or the zinc in your cells, was formed in such a star's death throes. We truly are made of stardust, scattered by stellar explosions billions of years before we were born. After a supernova, the core of the star might become a neutron star, or if the star was extremely massive, it might collapse entirely into a new black hole. Thus, the brilliant stellar explosion leaves behind, at its center, either a tiny dense object or an abyss of gravity. In either case, the material blown out enriches the space around it with heavy elements that will someday become part of new stars and planets. Supernovae are the universe's way of recycling matter, turning old stars into ingredients for new worlds. Some supernovae are even more powerful than typical. We call them hypernovae, and they can be associated with something called a gamma-ray burst. These occur when an exceptionally massive star collapses or when two neutron stars merge, creating an explosion so energetic that it emits narrow jets of gamma rays, the highest energy form of light. If one of those jets happens to point towards Earth, we detect a sudden, intense burst of gamma rays lasting a few seconds or minutes. A gamma ray burst is among the most energetic events in the universe. In those few seconds, it can release more energy than our sun will emit in its entire 10 billion year lifetime. Thankfully, gamma ray bursts that could affect Earth are exceedingly rare, and none are known nearby. They are generally in distant galaxies. So instead of posing harm, they serve as beacons telling us about catastrophic events across the cosmos. The universe is mostly kind to us. These cosmic fireworks are usually far, far away. Rather than danger, they bring information, clues about how massive stars live and die in galaxies millions or billions of light years distant. Stars come in many sizes and colors. Our sun is a fairly ordinary yellow-white dwarf star, middle-aged and steady. Smaller stars, called red dwarfs, glow dimly with a reddish hue and can live incredibly long, hundreds of billions or even trillions of years, far longer than the current age of the universe. Larger stars, blazing blue or white in color, burn very hot and bright but live short lives in comparison, sometimes just a few million years before they exhaust their fuel. The largest stars swell into red supergiants near the ends of their lives. One of the biggest known stars, UY Scuti, is so large that if it were placed where our sun is, its outer layers would extend out beyond the orbit of Jupiter. Such a star is enormous but also diffuse and relatively cool, hence its red color. These giants live fast and die young, likely ending in supernova explosions and leaving behind neutron stars or black holes. By contrast, the smallest true stars are only about 8% the mass of the Sun, just heavy enough to ignite nuclear fusion in their cores. If a forming star has less mass than that, it never truly turns on its stellar furnace. Such an object is called a brown dwarf, not quite a star, but not a planet either. Brown dwarfs glow only faintly with leftover heat, and maybe a touch of fusion of deuterium, a form of hydrogen, for a short time. They are like eternal embers, never bursting into full starlight. High above and around us, there are stars that wander alone in the darkness, flung from their homes. These are rogue stars, sometimes ejected by the gravitational slingshot of a black hole or by a close interaction in a multiple star system. They drift in intergalactic space, solitary travelers carrying the story of their lost galaxies. It's a poignant thought. A star, perhaps once part of a familiar galaxy, now destined to roam the silent void between galaxies forever. Our sun, and the entire solar system, orbits the center of the Milky Way at about 230 kilometers per second, over 800,000 kilometers per hour. Even at that astonishing speed, it takes roughly 225 million years to complete one circuit around the galaxy. This means the last time we were in our current position in the Milky Way, it was the age of the dinosaurs on Earth. In Earth terms, we've only gone around the galaxy about 20 times since our solar system formed approximately 4.5 billion years ago. One galactic year is a long, long time. Everything in space is moving. Even as you lie here quietly, listening to these words, the Earth is rotating on its axis and orbiting the Sun. The Sun is moving through the galaxy, and the Milky Way itself is drifting within its local group of galaxies. All motion is relative, and out in space, immense speeds can feel like stillness because of the vast scales involved. We don't feel the Earth hurtling through space, but it surely is. And even as we sleep, our planet continues its gentle, eternal motion. The Milky Way and the Andromeda Galaxy, our large galactic neighbor, are on a collision course. Don't worry, this cosmic event won't happen for about 4 to 5 billion years. When it does, though, it won't be a violent crash like cars on a highway. Instead, the two huge collections of stars will gradually merge in a grand, slow dance. The stars within them are so far apart that hardly any stars will hit each other directly. Over billions of years, the two galaxies will swirl together and form a new, larger galaxy, often nicknamed Milkomeda. In the night sky of the far future, any beings alive to see it would witness a breathtaking sight as Andromeda's stars smear across the sky and eventually mix with our own. Our galaxy has collided with and cannibalized smaller galaxies before. The Milky Way is built from the remnants of many smaller galaxies that it has pulled in over billions of years. Even now, the Milky Way is absorbing a small neighbor, the Sagittarius dwarf galaxy. Its stars are being pulled out into long streams that wrap around our galaxy. If you could see those streams in the sky, they'd form faint rivers of stars. Galaxies grow by merging, and our own carries the ghosts of many smaller systems that became part of the whole. Not all galaxies are majestic spirals like the Milky Way. Some are elliptical galaxies, large, oval or spherical collections of stars that can be much bigger than spirals but with no distinct arms or much gas for new stars. Others are irregular galaxies with no clear shape at all, often because they've been distorted by interactions or mergers. And there are countless dwarf galaxies, small and faint, swarming around larger galaxies. The universe has galaxies of all sizes and forms, each shining with the collective light of millions or billions of stars. The space between galaxies is not completely empty. It's threaded with extremely thin gas, and on larger scales, galaxies are arranged in a kind of cosmic web. Imagine galaxies as sparkling beads on invisible threads, and between those threads are immense dark voids with few galaxies. This structure formed over time as gravity pulled matter into filaments. It's beautiful to consider. On the grandest scales, the universe looks a bit like a web or sponge, with chains of galaxies and huge empty chambers. We live on one tiny strand of this cosmic web. One of the largest structures ever observed is something called the Hercules Corona Borealis Great Wall. It's an immense cluster of galaxy clusters, stretching billions of light years across. Discoveries like this challenge our understanding because on such enormous scales we expect the universe to be roughly uniform. Structures that huge make us wonder if we have the full picture, or if our cosmic maps still hold surprises. They remind us that on scales almost too vast to imagine, matter isn't evenly distributed. Gravity has sculpted some extraordinarily large patterns. Somewhere in the direction of the constellation Centaurus, a great unseen mass is tugging on us and on many of our galactic neighbors. We call it the Great Attractor. It lies about 200 million light-years away, hidden behind the Milky Way's dense, starry disk, which makes it hard to observe directly. But we feel its pull. Our entire local group of galaxies, including the Milky Way and Andromeda, is moving toward that region of space. We aren't certain exactly what the Great Attractor is, likely a huge cluster of galaxies or perhaps a confluence of dark matter, but it's a reminder that unseen structures can exert profound influence. In the cosmic neighborhood, even things we haven't mapped can affect the motion of galaxies like ours. Dark matter is one of those unseen influences. When we measure how galaxies rotate, we find their outer regions orbit far faster than they should if only the stars and gas we see were providing the gravity. It's as if an invisible halo of mass surrounds each galaxy, adding extra gravitational pull. We call this unknown mass dark matter. It doesn't emit or absorb light, yet it outweighs all the normal matter, stars, gas, dust, by roughly a factor of 5. Its nature remains one of the deepest mysteries in science. Perhaps dark matter is some new kind of particle swarming around galaxies, or maybe our understanding of gravity needs an adjustment on large scales. Either way, dark matter acts as the invisible scaffolding that holds galaxies and galaxy clusters together. One leading idea is that dark matter consists of particles that barely interact with normal matter at all. Billions of them might be passing through your body every second without you ever noticing. Scientists have built sensitive detectors deep underground to try to catch a glimpse of a dark matter particle. But so far, these particles remain elusive. They're like cosmic ghosts. We see their gravitational effects everywhere, but we have yet to directly detect a single one. Just as mysterious as dark matter is something even more dominant: dark energy. While dark matter pulls things together with gravity, dark energy seems to be doing the opposite, pushing the universe apart. About 68% of the universe, by energy content, appears to be this dark energy. It's the name we give to whatever is causing the expansion of the universe to speed up. For billions of years after the Big Bang, cosmic expansion was slowing down, gradually decelerating due to the pull of gravity. But about 5 billion years ago, that changed. Expansion started to accelerate. Galaxies began to push away from each other faster and faster. We attribute this cosmic second wind to dark energy, a mysterious effect associated with the vacuum of space itself. We don't know exactly what dark energy is. It could be a property of space, often thought of as the energy of empty space, or a new field or force. But we see its effects. The universe's expansion is getting faster. Dark energy now drives the evolution of the cosmos on the largest scales, even though we only perceive it indirectly. The accelerating universe means that in the distant future, galaxies outside our local group will slip beyond our view. As space expands faster and faster, their light will no longer reach us. Hundreds of billions of years from now, a future astronomer in our galaxy might see nothing beyond the Milky Way and its merged neighbors. All other galaxies' light will have stretched and faded away. We live in a time where we can still observe countless galaxies, a time rich in cosmic information. Far in the future, the universe will appear much emptier to any observers that might be around, simply because so much has rushed out of sight. The universe began about 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space. It was an expansion of space itself from an initially hot, dense state. In the first moments, the universe was an extremely hot soup of particles and energy. As it expanded, it cooled, eventually allowing particles to combine into the first simple atoms, hydrogen and helium mostly. We can still detect a faint afterglow from that early time. It's all around us as a very soft glow of microwaves called the cosmic microwave background, CMB. This light comes from when the universe was only 380,000 years old, a baby, cosmically speaking, and it marks the moment when the hot plasma of the early universe cooled enough to become transparent. The CMB is almost uniform, only varying by tiny fractions of a degree in temperature across the sky. This near uniformity is a puzzle. How did different far-apart regions of the young universe know to have the same temperature? The leading explanation is that in the universe's first instance, there was a brief period of ultra-rapid expansion called inflation. If our entire observable universe was once a tiny, uniform region that then inflated exponentially fast, it would explain why the CMB looks so even. Those regions were once close together and had time to equalize their properties. Inflation is an elegant idea that fits many observations, though it happened so early, a tiny fraction of a second after the Big Bang, that it's hard to test directly. Still, the patterns in the CMB's faint ripples are consistent with something like inflation having occurred, stretching space tremendously in the blink of an eye. Another puzzle from the early universe is why there is more matter than antimatter. In theory, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other completely, leaving nothing but energy. Clearly, that didn't happen. Because we are here, somehow matter gained a slight edge. For roughly every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny surplus, 1 in a billion, is what remained after all the annihilation, and it became all the galaxies, stars, planets, and people. What caused this asymmetry in the early universe? We're not sure. It likely involves subtle physics beyond what we currently know, perhaps tied to the behavior of certain particles in the first moments after the Big Bang. It's a deep mystery. Why does anything at all exist? Because if matter and antimatter had been perfectly balanced, they would have canceled out completely, and the universe would be full of light, but no atoms. Instead, we have a cosmos full of matter, luckily for us. As the early universe expanded and cooled, the first stars likely formed when it was only a few 100 million years old. These first stars, we call them population 3 stars, would have been made almost purely of hydrogen and helium, since heavier elements didn't exist yet. They were probably very massive and short-lived, burning hot and dying in supernova explosions that enriched the surrounding gas with the first heavy elements. Those heavy elements, like carbon, oxygen, silicon, etc., then allowed later generations of stars to form with planets around them. We haven't yet observed a population 3 star directly. They would be long gone by now. But we see indirect evidence. We find ancient second-generation stars that contain extremely low amounts of heavy elements, suggesting they formed from material that had been only lightly polluted by the very first stars. We have discovered some of those ancient stars in our own galaxy's halo, stars almost as old as the universe itself. They wander in long, tilted orbits around the Milky Way. By analyzing their light, astronomers find they have almost no elements beyond hydrogen and helium. They are essentially fossils of the early universe, living relics from a time before heavy elements were common. One such star, often nicknamed the Methuselah star, appears to be around 13 billion years old. Studying these primordial stars is like reading the childhood history of the cosmos, written in faint starlight. Galaxies grew over time. In the early universe, there were only small proto-galaxies, little clumps of stars and gas. Over billions of years, gravity drew these together to form larger galaxies. Our Milky Way, for example, assembled from many smaller pieces long ago. We see evidence of those mergers in our halo. Streams of stars that don't quite fit the main disk, remnants of devoured dwarf galaxies. The universe built big galaxies from smaller ones, somewhat like Lego blocks, clicking together over time. And galaxies continue to evolve. They collide, merge, or get tugged by neighbors, slowly changing over cosmic time. Some galaxies in the very distant universe, meaning we see them as they were not long after the Big Bang, appear surprisingly mature or massive for their age. The James Webb Space Telescope, with its powerful infrared vision, has identified galaxies from when the universe was only a few 100 million years old that seem more developed or larger than expected. These observations have astronomers excited and a bit puzzled. It suggests stars and structures formed quickly in some spots, and we may need to adjust our models of early galaxy formation. We are peering farther back than ever, and the early universe is turning out to have a few surprises up its sleeve. Quasars are among the brightest objects in the universe and were a big mystery when first discovered. A quasar looks like a star-like point of light, but it is actually the extremely luminous core of a distant young galaxy. At the center of a quasar is a supermassive black hole voraciously consuming matter. As gas and stars fall toward the black hole, they form a hot accretion disk around it and emit extraordinary amounts of energy. Quasars can outshine their entire host galaxies. They are so bright we can see them across billions of light years. Some quasars we see today are from when the universe was only a few billion years old. The energy output of a quasar defies imagination. The brightest quasars shine with the power of trillions of suns. We have found quasars so distant that their light began its journey when the universe was less than 1 billion years old. That's over 13 billion years ago. These quasars are powered by black holes already billions of times the mass of the Sun at that young age. How did such black holes grow so big so fast? It remains an open question in astrophysics. Perhaps they started from seed black holes that were themselves much more massive than typical stellar remnants. Or maybe they grew via frequent mergers or episodes of super-Eddington accretion, a fancy term for very rapid feeding. It's an ongoing area of research. The early universe clearly formed some monsters in a hurry. Not all supermassive black holes are active like quasars. Many, like the one in our Milky Way center, are relatively quiet most of the time, but they can flare to life if something disturbs them, say a big cloud of gas or a star wanders too close. For example, in 2019, astronomers observed a star in a distant galaxy get too close to its galaxy's central black hole and get torn apart, a so-called tidal disruption event. The shredded star's material spiraled into the black hole, creating a bright flare of light, which telescopes caught. It was a stark reminder of the dark, hidden appetite lurking at the center of galaxies. Most of the time, stars orbit safely, but straying too near a supermassive black hole can be a fatal mistake for a star. Black holes can also emit spectacular jets of particles and energy when they are actively feeding. In some galaxies, especially radio galaxies and quasars, the central black hole's accretion disk and magnetic fields work together to launch twin jets at nearly light speed, shooting out far beyond the galaxy itself. These jets can extend for hundreds of thousands of light years, glowing in radio waves and sometimes visible light as they plow into intergalactic space. It might seem paradoxical, black holes, which trap light, ending up powering jets that radiate brightly. But the trick is that the stuff emitting the light in jets is outside the black hole, accelerated by the black hole's gravitational and magnetic fury before it crosses the point of no return. Although space is mostly quiet vacuum, when these enormous jets slam into surrounding gas, they create vast lobes of hot, radiating plasma. Entire galaxy clusters can be filled with a faint radio glow from the cumulative jets of past active galactic nuclei AGN. In this way, black holes, ostensibly objects of pure darkness, can light up the cosmos and even regulate the growth of galaxies. The energy they pump out can heat surrounding gas and prevent too many stars from forming at once. So black holes don't just sit quietly. They can influence their whole galaxy's fate. The universe has a grand symmetry on large scales. No matter which direction we look, distant galaxies on average are receding from us. This is not because we're at the center of the universe, but because space itself is expanding uniformly. If you were in a galaxy 1 billion light years away, you'd observe the same thing, all other galaxies moving away. This is the essence of the Big Bang model. Not an explosion from a center, but an expansion of every region of space. Galaxies are carried apart like raisins in a rising loaf of bread. As a consequence of this expansion, distant galaxies are redshifted. Their light is stretched to longer, redder wavelengths by the time it reaches us. The farther away a galaxy is, the more its light is redshifted. For extremely distant galaxies, the light is shifted completely out of the visible spectrum into infrared or radio waves. That's why telescopes like Webb, which see infrared, are needed to observe the earliest galaxies. Their visible light has been shifted into infrared by the long journey through expanding space. Because light has a finite speed and the universe has a finite age, there is a cosmic horizon beyond which we cannot see. Our observable universe is a bubble. currently about 93 billion light-years in diameter, inside the whole universe. There may be much more beyond what we can see, perhaps an infinite expanse, but light from those regions has not had time to reach us in 13.8 billion years. In that sense, the observable universe is like a tiny patch of a possibly much larger reality. We don't know if the universe is finite or infinite. It might wrap around itself in a higher dimension, somewhat like how the 2D surface of Earth is finite but has no edge, or it might go on forever. Current observations show space is very close to flat in geometry, which if it's finite would imply a size far larger than we can see. Whether infinite or just extremely vast, the universe is certainly bigger than our minds can easily grasp. Just 66 million years ago, a blink in cosmic terms, a large asteroid struck Earth and contributed to the mass extinction that ended the age of the dinosaurs. Such impacts are reminders that even local cosmic events can dramatically change the course of life on a planet. These events are rare on human timescales, but over millions of years, many can occur. Earth bears the scars of some ancient impacts, like the crater from the dinosaur-killing asteroid off Mexico's coast. The cosmos isn't actively hostile, but it isn't entirely gentle either. Over long periods, occasional events like impacts or supernova blasts nearby can influence the trajectory of life. There are millions of asteroids in our solar system. Most orbit safely in the asteroid belt between Mars and Jupiter. Jupiter's gravity, in fact, has a big influence. It can perturb the orbits of comets and asteroids. In one sense, Jupiter serves as a shield, often flinging comets away or swallowing them. But in another sense, its gravity can also send some our way. It's a double-edged role. Over Earth's history, impacts have happened and shaped evolution, perhaps even delivering water and organic materials, and also causing extinctions. Our solar system is not a static place. It's dynamic, with planets and asteroids interacting over eons. Beyond Neptune lies the Kuiper Belt, a region of icy, rocky bodies left over from the formation of the solar system. Pluto is one of these larger Kuiper Belt objects. These distant worlds are in deep freeze, illuminated only dimly by the sun. Occasionally, one of these icy bodies is perturbed and falls inward as a long-period comet. And much farther out, extending perhaps tens of thousands of times farther than Pluto, is the hypothetical Oort cloud, a vast reservoir of comets in an enormous sphere around our solar system. No one has observed the Oort cloud directly. The comets are too small and far, but the long-period comets that occasionally grace our skies likely come from this distant cloud, nudged by a passing star or galactic tide to begin a journey toward the sun. Voyager 1, a spacecraft launched in 1977, has now traveled farther than any other human-made object, over 14 billion miles, around 23 billion kilometers, from Earth. It has left the bubble of our sun's influence, the heliosphere, and entered interstellar space. It carries a famous golden record, a phonograph record containing sounds and images of Earth, intended as a cosmic message in a bottle. Voyager 1 will wander the galaxy essentially forever, or until it possibly enters a star or planet far, far in the future. In about 40,000 years, it will pass within a couple of light years of another star. Even so, the odds of it ever being found by another civilization are extremely small, but the poetry of it is profound. A tiny craft with a greeting from Earth, drifting silently in the starry sea. If you were to shrink the entire solar system, out to Neptune, to the size of a coffee cup, the Milky Way would still span a size larger than North America, and the Milky Way is itself just one typical galaxy. These analogies show just how vast the cosmos is beyond our local space. It can be dizzying to consider such scales, but it can also be comforting. Many of our daily worries seem smaller against the grand backdrop of the stars. It's often said that we are made of star stuff, and this is quite literally true. The carbon in your muscles, the calcium in your bones, the oxygen you breathe, those atoms were forged in stars that lived and died billions of years ago. The iron in your blood was formed in a supernova explosion. The gold in your jewelry was likely created in the collision of two neutron stars. We carry the history of the cosmos within our bodies. Every atom of heavier elements was once inside a star. We are a way for the universe to know itself, composed of the ashes of long-dead suns. In fact, the very early universe contained only the lightest elements, mainly hydrogen and helium, with a dash of lithium. All the heavier elements, the ones essential to planets and life, carbon, nitrogen, oxygen, and so on, had to be manufactured by stars through nuclear fusion and then spread through space by stellar winds and supernovae. So the universe had to age a bit and go through generations of stars before planets like Earth, with its richness of elements, could form. In a sense, the universe became aware of itself through beings like us only after stars had time to cook up the complex elements needed for life. There's a beautiful region in our night sky called the Orion Nebula, visible as a fuzzy patch in Orion's sword. This is a vast stellar nursery, a cloud of gas and dust where new stars are being born. Through a telescope, it glows with a gentle greenish-pink light, illuminated by the young hot stars inside it. Within those clouds, gravity is gathering pockets of gas that will ignite into newborn suns. Perhaps planets are coalescing around those infant stars too. Nebulae like Orion are often called cosmic nurseries or maternity wards of stars. They are among the most peaceful and inspiring sights in the sky, creation amid the darkness. When stars like our sun reach the end of their lives, in several billion years, they don't explode. They gently shed their outer layers into space, creating what's known as a planetary nebula, a bit of a misnomer as they have nothing to do with planets. The star's core contracts into a small, hot white dwarf, while its outer layers expand outward and form a glowing shell of gas. These shells often take on delicate, ring-like or bubble shapes, fluorescing in pastel colors under the light of the dying core. They last only tens of thousands of years before dispersing into the interstellar medium. One day, our sun may produce such a nebula, a final beautiful act, casting much of its substance back out to the cosmic recycling system. One day, our sun will indeed become a white dwarf. After it exhausts its fuel, it will swell into a red giant, perhaps engulfing the inner planets. Then it will eject its outer layers, forming a nebula, and the remaining core will shrink down to roughly the size of Earth, but incredibly dense. That white dwarf will be initially extremely hot and luminous, in ultraviolet light, but with no new nuclear fuel, it will gradually cool and fade over trillions of years. The sun's gentle warmth and light will be a memory etched in the white dwarf's cooling glow. Fortunately, this fate lies about 5 billion years in the future, so there is no immediate concern for us. However, long before that, the sun's gradual changes will affect Earth. In roughly 1 billion years, the sun is expected to be about 10% brighter than it is now. That may not sound like much, but it likely would make Earth too hot for liquid water in the long run. The oceans would evaporate or be pushed to the poles, and a runaway greenhouse effect could take hold, similar to what happened on Venus. Life as we know it would be in trouble long before the sun becomes a red giant. By 5 billion years from now, when the sun does swell into a red giant, it may engulf Mercury and Venus, and possibly Earth as well. There's some uncertainty whether Earth will be swallowed or just scorched. But these changes happen on timescales so immense that it's almost beyond comprehension. If humanity or our far descendants are still around even a few million years from now, technology might allow moving elsewhere. In any case, The impermanence of even something as steady as the sun is a humbling thought. Solar eclipses are one of nature's great coincidences and spectacles. Our moon, though 400 times smaller in diameter than the sun, is also about 400 times closer to us. So the sun and moon appear nearly the same size in Earth's sky. This allows the moon to completely cover the sun during a total eclipse. For a few magical minutes, day turns to deep twilight. Bright stars and planets become visible in the sky, and the sun's delicate corona, its hot outer atmosphere, shines around the black disk of the moon like a pearly halo. Birds may hush as if nightfall came, and the temperature drops. Total solar eclipses are rare at any given spot on Earth, and historically they inspired awe and sometimes fear. Today we understand them, but they remain breathtaking, a cosmic alignment that produces one of the most beautiful sights in the sky. Over time, the moon is actually slowly drifting away from Earth by about 3.8 centimeters, 1.5 inches, per year. In the distant future, it will no longer appear large enough to completely cover the sun. That means hundreds of millions of years from now, Earth will no longer experience total solar eclipses, only partial ones, where a ring of sun is always visible around the moon. We happen to live in an epoch where total eclipses are possible, a lucky fluke of timing and distances. Our distant descendants, or whoever is around in that far future, might never see the sun's corona revealed by a moon eclipse. So it's something to cherish about our era of Earth's history. The moon itself likely formed through a titanic collision in the early solar system. The theory goes that about 4.5 billion years ago, when Earth was very young, it was struck by a Mars-sized protoplanet. This catastrophic impact ejected a huge amount of debris into orbit around Earth, which eventually coalesced to form the moon. This explains why the moon's composition, especially in its crust, is similar to Earth's outer layers. It also accounts for why the moon is relatively large compared to Earth. It's essentially made of material splashed out of Earth's mantle. Our serene moon may thus be the child of a violent event, a reminder that even peaceful skies can have dramatic origins. Because of tidal locking, the moon always shows the same face to Earth. For thousands of years, humans wondered what was on the moon's far side, the side we never see. It wasn't until 1959 that a Soviet spacecraft finally photographed the moon's far side, revealing it to be heavily cratered and quite different from the near side, which has large, dark lava plains we call seas. Now, we know the whole moon, but for most of human history, half of our companion world was forever hidden, a permanent mystery until the space age. Standing on the moon and looking up at the sky, you'd see blackness, even when the sun is shining. The moon has essentially no atmosphere, so there is no air to scatter sunlight and create a blue sky like we have on Earth. During the lunar daytime, the sun blazes in a black sky, and stars can be seen even when the surface is lit. Though the sun's glare can make it hard, you'd at least see the brighter stars and planets if you shielded your eyes. Apollo astronauts experienced this stark view, a pitch-black sky arching over a gray sunlit landscape. On the moon, Earth would appear as a large blue and white marble hanging in the sky, about 4 times the apparent diameter of the moon we see from Earth. And because the moon keeps one face toward us, Earth would remain in nearly the same spot in the lunar sky, not rising or setting, except a slight wobble. Astronauts on the moon marveled at the sight of Earth. One of the most iconic photos, Earthrise, was taken by Apollo 8 astronauts as they orbited the moon. It shows our planet cresting above the moon's horizon, a delicate sphere of blues and whites in the blackness of space. Seeing Earth from afar gave those astronauts, and many who saw the photo, a deep appreciation for our planet's fragility and unity. Our solar system is full of wonders. Consider Saturn, with its magnificent rings. Those rings are made of countless icy particles, ranging in size from dust grains to boulders, orbiting around Saturn's equator. They form a broad, thin disk that would stretch from Earth to the Moon if laid flat, yet in some places the rings are only a few tens of meters thick. They might be the remnants of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Saturn's rings won't last forever. They are slowly drifting inward, and Saturn's gravity will eventually pull them down into the planet over the next 100 million years or so. We are fortunate to live at a time when Saturn's rings are wide and bright. Future distant generations might know a Saturn without its beautiful halo. At Saturn's North Pole, there is a strange and striking phenomenon, a vast cloud pattern in the shape of a hexagon. This six-sided jet stream was first clearly seen by the Voyager spacecraft in the 1980s and later studied in detail by the Cassini probe. The hexagon is large enough to fit 4 Earths across and rotates with a period roughly equal to Saturn's day, about 10.5 hours. Scientists suspect it's a standing wave in Saturn's atmosphere, basically a deep weather pattern, but it's still not entirely understood. It's amazing to realize nature drew a geometric shape on a planet's pole. Saturn's hexagon is one of those reminders that the cosmos still holds playful secrets in even its weather systems. Jupiter, the largest planet, has its own impressive features, most famously the Great Red Spot, a gigantic storm like a hurricane, but larger than the Earth, that has been raging for at least 300 years. The Great Red Spot is a reddish oval in Jupiter's cloud tops, and it has been observed to shrink a bit in recent decades but is still enormous. Jupiter's atmosphere is dynamic, full of banded clouds and storms. The energy powering these long-lived storms may come from Jupiter's internal heat, as Jupiter radiates more heat than it gets from the Sun, combined with the planet's rapid rotation. Jupiter also has an enormously strong magnetic field, the strongest of any planet in our solar system. It traps charged particles in intense radiation belts around the planet. The environment near Jupiter is harsh with radiation, which is something space probes have to be built to withstand. This magnetic field also generates brilliant auroras at Jupiter's poles, far larger and more powerful than Earth's auroras. Even some of Jupiter's moons, like the volcanic moon Io, contribute to the light shows. Io's volcanoes spew material that gets ionized and funneled along Jupiter's magnetic field lines, creating auroral spots. Jupiter is like a miniature solar system with its own complex interactions between the planet, its magnetic field, and its moons. Some of Jupiter's moons are among the most intriguing places in the solar system for potential life. For example, Europa, a moon of Jupiter roughly the size of our moon, has a thick shell of ice covering what is almost certainly a global ocean of liquid water beneath. Tidal forces from Jupiter flex Europa's interior, keeping it warm enough for water to stay liquid under the ice. Where there is water and a source of energy, there might be life. We have yet to drill through Europa's ice, but upcoming missions will investigate further. Scientists sometimes imagine fish-like creatures or microbial life in those dark waters, but for now it remains a speculation that tickles our imagination as we lull to sleep. Another moon with an ocean is Saturn's Enceladus. This small, bright moon surprised everyone when the Cassini spacecraft saw geysers of water vapor and ice particles shooting out from cracks near its south pole. Enceladus, like Europa, has a subsurface ocean beneath its ice crust. Cassini flew through those plumes and detected organic molecules and hints of hydrothermal activity in the moon's ocean. Enceladus essentially has a tiny version of environments akin to Earth's deep-sea hydrothermal vents, where life on Earth might have begun. It's one of the most promising places to search for microbial life in our solar system. Imagine a warm ocean floor, dark except for the glow of chemical reactions, perhaps dotted with alien microorganisms. all enclosed under kilometers of ice, on a little moon orbiting a ringed planet. It's a quiet, speculation-inducing scene, perfect for nighttime pondering. Titan, Saturn's largest moon, is another world that captivates the imagination. Titan is often likened to a primordial Earth in deep freeze. It has a thick nitrogen atmosphere with a hint of orange smog from complex organic molecules. And remarkably, Titan has rivers, lakes, and seas on its surface, but instead of water, they are filled with liquid methane and ethane, which are gases on Earth but liquid in Titan's frigid approximately negative 180 degrees Celsius temperature. Titan's landscape includes dunes of hydrocarbon sand, carved channels, and possible cryovolcanoes, volcanoes that spew cold slurries of water and ammonia. When the Huygens probe landed on Titan in 2005, it saw rounded pebbles made of water ice, essentially rocks in Titan's conditions. Some scientists even speculate that exotic life could exist in Titan's methane lakes, using chemistry very different from life on Earth, though no evidence of that yet. Titan is a reminder that worlds can be Earth-like, with weather, rivers, lakes, yet utterly alien in their composition and chemistry. We have found over 5,000 exoplanets, planets around other stars, and they display an astonishing variety. Some are hot Jupiters, giant gas planets that orbit scorchingly close to their stars, closer than Mercury is to our Sun. These giants are so hot that some have upper atmospheres that boil off into space. They were a surprise to scientists because our solar system has nothing like them, and their existence forced us to rethink how planetary systems form and evolve. There are exoplanets with truly bizarre environments. One example is a planet called HD 189733b, a gas giant where it might rain molten glass sideways and howling 7,000 kilometers per hour winds. The planet's atmosphere contains silicate particles which, at high heat, could condense into tiny glass droplets that scatter blue light, giving the planet a beautiful cobalt color and possibly creating glass rain. Another exoplanet, WASP-12b, is so close to its star that its day side is heated to over 2,000 degrees Celsius, and the entire planet is stretched into an egg shape by tidal forces, with material bleeding away to the star. And there's Kepler-7b, a planet where clouds might be made of rock vapors that condense into gemstones, meaning it could literally rain rubies and sapphires, crystallized corundum in its upper atmosphere. The cosmos has wild weather beyond our imaginations. Some exoplanets are tidally locked to their stars, meaning one side of the planet always faces the star, endless day, and the other side is in perpetual night. Many planets orbiting red dwarf stars are like this, since they orbit very close. On such a world, the day side might be scorching while the night side is frozen. But in between, along the terminator, the line between day and night, there could be a ring of temperate twilight, a place of eternal sunset that could be more hospitable. It's fascinating, and a bit dreamy, to consider a world where if life existed, perhaps it would thrive in that perpetual dawn-dusk ring around the planet. One of the most intriguing exoplanets discovered so far is Proxima Centauri b. It orbits Proxima Centauri, the closest star to our Sun, a red dwarf just 4.24 light-years away. Proxima b is at a distance from its small, cool star that could allow liquid water on its surface. It lies in the so-called habitable zone. The planet is a bit more massive than Earth and orbits its star every 11 days. Since the star is much dimmer than the Sun, that close orbit still puts it in a temperate zone. We don't yet know if Proxima b has an atmosphere or oceans. It might be tidally locked, and Proxima Centauri is known to produce powerful flares that could strip a planet's atmosphere. Still, Proxima b is essentially next door in cosmic terms, and it's tantalizing to think that the nearest potentially Earth-like planet is right around the corner, astronomically speaking. Perhaps someday far in the future, humans, or our robotic emissaries, will visit it. The TRAPPIST-1 system, about 39 light-years away, has 7 known planets roughly the size of Earth orbiting a tiny red dwarf star. What's remarkable is that 3 of these 7 worlds lie in the star's habitable zone, where temperatures could allow liquid water if conditions are right. These planets all orbit extremely close to their dim star, with years that are only a few days long, and they are likely tidally locked. The entire system is like a miniature solar system crammed into a space smaller than Mercury's orbit. The idea that 3 potentially habitable planets are dancing around one small star is astonishing. If life can emerge in such conditions, that system could host multiple living worlds, perhaps all influencing each other's development in some way. It's a delightful thought to lullaby the mind, a sky where sister planets loom large, and maybe, just maybe, multiple surfaces where life gazes up and sees the same red star. For all the thousands of exoplanets discovered, we haven't yet found definitive signs of life beyond Earth. We keep searching in various ways, listening for radio signals, looking for telltale gases like oxygen or methane in exoplanet atmospheres, and pondering indirect hints. The silence so far, despite the vast number of planets, leads to the Fermi Paradox. The galaxy is old and large. If intelligent life is out there, shouldn't we see some evidence of it by now? There are many possible answers, ranging from life, or at least intelligent life, is extremely rare, to civilizations are common but don't last, long to they're out there but hiding or uninterested as you drift to sleep. It's interesting, and not troubling, I hope, to consider that we might be, at least for now, effectively alone, or at least isolated, in this corner of the cosmos. And that makes our existence all the more precious. We have been sending out radio signals for about a century, which means a bubble of radio waves roughly 100 light-years in radius is expanding out from Earth. Only stars within that bubble could potentially know we exist by detecting our early broadcasts, and even then, deciphering them would be incredibly hard. Our galaxy is about 100,000 light-years across, so our presence is currently only known, potentially, to a few hundred stars out of billions. Any hypothetical aliens beyond that distance won't yet have heard from us. Space is immense and communication is slow at the speed of light. It's no surprise we haven't chatted with ET. Our cosmic hello has only traveled a tiny fraction of the Milky Way so far. On the flip side, if another civilization is broadcasting, their signals have to travel and reach us as well. We've been listening for decades through SETI, the search for extraterrestrial intelligence, aiming radio telescopes at the stars to catch any unnaturally patterned signals. So far, nothing definitive has been heard. We did catch one strong, unexplained signal back in 1977, the famous WOW signal, a powerful narrowband radio signal that appeared once and never repeated. It lasted for 72 seconds, and the astronomer who spotted it scribbled "WOW" next to the data printout. To this day, we don't know if it was a glitch, a one-time natural event, or perhaps an artificial signal from a distant civilization that just happened to flash by. It's tantalizing and remains unexplained, but without a repeat, it's an unsolved whisper from the stars. Humanity has also deliberately sent messages and mementos into space, just in case someone finds them. In the 1970s, we launched the Pioneer and Voyager probes, each carrying plaques, and, in Voyager's case, a golden record, with information about Earth, our location, images and sounds of our world, greetings in many languages, and music. They are like bottles cast into the cosmic ocean. The chances of them being found soon are extremely slim, but they will wander the galaxy for millions of years. Even if they're never found, it's comforting to know that a little piece of us, our curiosity and goodwill, is out there traversing the stars. If an alien civilization is far more advanced than ours, their technology might be completely beyond our recognition. They might communicate in ways we can't detect or inhabit forms we wouldn't easily notice, like AI minds in machines or swarms of microscopic devices or something living mostly in mathematics and quantum fields. Who knows? It's possible that truly advanced beings might dwell on scales or in mediums that render them effectively invisible to us. Some thinkers have even imagined that sufficiently advanced civilizations could harness energy on the scale of galaxies or upload themselves into virtual realms. These are wild speculations, of course. We have no evidence of anything like that. But when pondering the cosmos at bedtime, it's fun to allow some daydreams or night dreams of worlds with technology akin to magic, and to realize that we humans are just taking our first small steps into the cosmic ocean. A speculative idea that captures the imagination is that an advanced civilization might build a Dyson sphere, a megastructure encircling its star to capture as much energy as possible. If one existed, it might look to us like a star that periodically dims strangely or emits an unusual infrared signature. A few years back, a star named Tabby's star, KIC 84622852, was observed to have very odd, irregular dips in brightness. Some hypothesized it might be due to an incomplete Dyson sphere or some kind of giant artificial structure blocking the star's light. The more we studied Tabby's star, the more it seemed likely the cause was natural, perhaps a swarm of dust or comet fragments. But for a time, we all playfully speculated about alien megastructures. That star still hasn't yielded a fully agreed-upon explanation for its weird behavior, which is okay. The universe often leaves us with questions. Tabby's star reminded us that we must keep an open mind. While aliens were an extraordinary leap, the mere suggestion made everyone pay attention and wonder, which is a kind of fun cosmic mystery in itself. Another cosmic mystery involved a star that literally vanished. In a galaxy called PHL 293b, a very massive luminous star was observed over many years, and then around 2015 it was noted that the star was just gone. It hadn't gone supernova, which we would have seen. It simply wasn't visible anymore. One possibility is that it collapsed directly into a black hole without an explosive fireworks show, essentially a failed supernova. Another is that it became dim, perhaps shrouded by dust after a big eruption. If the direct collapse idea is true, it would be the first time we've seen a huge star just quietly disappear into a black hole. How oddly fitting and quiet would that be? A star that lived loudly, died silently. Astronomers will continue to check that galaxy for signs of either a hidden star or a new black hole. Our own solar system has its share of unsolved puzzles. One current curiosity is whether there's an unknown large planet far beyond Neptune, a hypothetical Planet 9. Certain distant icy objects, way out in the Kuiper Belt, have orbits that seem clustered in a way that suggests the gravity of something big, perhaps 5 to 10 times Earth's mass, might be hurting them. No such planet has been seen yet, despite searches. It would be faint and slow-moving out there, taking thousands of years to orbit. It might also be lurking in parts of the sky that are difficult to survey, perhaps toward the Milky Way's dense star fields. It's an ongoing detective hunt. If it exists, this large planet would be so far out that sunlight is feeble, and it might have an environment more akin to a cold mini-Neptune. If it doesn't exist, we'll have to explain those odd orbits another way. But isn't it thrilling that in our own backyard there might be a hidden planet yet to be discovered? Speaking of worlds discovered and then undiscovered, Pluto was long considered the 9th planet until it was reclassified as a dwarf planet in 2006, after many other similar icy worlds were found. When the New Horizons spacecraft flew by Pluto in 2015, We finally saw this distant world in detail, and it was breathtaking. Pluto has a heart-shaped bright region of nitrogen ice, smooth plains with no craters, indicating young surfaces, tall mountains of solid water ice capped with red organic compounds, and thin blue hazes in its atmosphere. It even has weather of sorts, thin atmosphere that can snow and form frosts. We learned that even a small world approximately 5.9 billion kilometers from the Sun can be geologically alive. It has likely a subsurface ocean or at least slush under its ice in some regions, and it certainly has ongoing processes that refresh its surface, perhaps slow convection of nitrogen ice. Pluto, once just a speck in our telescopes, turned out to be a complex, dynamic little world. A reminder: don't judge a planet by its size or distance. Even the far, cold ones have surprises. Comets are like time capsules, primitive icy leftovers from the formation of the solar system. When their elongated orbits bring them close to the Sun, their ice warms and turns into gas, creating those beautiful tails that can stretch millions of kilometers. Ancient peoples sometimes feared comets as omens, but now we see them as portals to understanding the early solar system. We've even visited a comet. The Rosetta spacecraft orbited Comet 67P and dropped a small lander, Philae, on it. We found that comets are very dark, covered in complex carbon-rich compounds, and they emit jets of gas as they heat up. Comets likely delivered some water and organics to the early Earth, aiding the origin of life. So when you see a comet softly glowing in the night, with its tail pointing away from the Sun, consider that it's a traveler from the solar system's deep freeze, possibly carrying whispers of our own beginnings. We often imagine space as silent and empty, but space is filled with fields and particles, and it can carry sounds of a sort. Not sound waves in air, but electromagnetic waves and vibrations in plasma that we can convert to audio. Planets and moons with magnetic fields and atmospheres produce radio emissions and plasma waves that, when processed, sound eerie and beautiful. For instance, the chorus of Earth's magnetosphere sounds like birds chirping at dawn, called the dawn chorus, and Saturn's radio emissions sound like a spooky, whooshing howl. NASA has released recordings of these converted signals, effectively the songs of the planets. The universe has a soundtrack. It's just beyond our ears' direct reach, but it's there if you have the right instruments. Throughout space, even empty regions aren't truly empty. Quantum physics tells us that what we think of as a vacuum seethes with temporary particles flickering in and out of existence. This constant quantum simmer might seem abstract, but without it, atoms themselves wouldn't hold together quite the same. Some scientists think the energy of empty space, these incessant quantum fluctuations, is related to the dark energy causing cosmic acceleration. It's as if even nothingness contributes to the grand evolution of the universe. Imagine that. The void is not void at all, but a foundation humming with possibility. As we mentioned earlier, gravity can even affect time. Near a massive object or at high speeds, time actually flows more slowly compared to an outside reference. We've measured this with precise clocks. An atomic clock on a fast jet or a satellite ticks a tiny bit slower than one on Earth's surface. Astronauts on the International Space Station age microseconds less over 6 months than people on the ground. These differences are minuscule for us, but if you could travel near the speed of light or linger near a black hole, you could leap far into the future compared to those you left behind. It's a form of one-way time travel to the future, allowed by Einstein's theory of relativity. While sci-fi often imagines machines and paradoxes, the universe's real time warp is more subtle and poignant. Time is elastic, and we all experience our own slightly unique flow of it. Cosmologists have pondered the ultimate fate of the universe. One scenario, which current evidence suggests, is an ever-expanding cosmos cooling into a big freeze or heat death. In this future, Galaxies accelerate away, stars age and die, new star formation dwindles as gas is used up or locked in remnants, and the universe, trillions upon trillions of years from now, becomes a dark expanse with faint embers, white dwarfs cooling to black, neutron stars and black holes persistently orbiting in an almost empty void. Eventually, even black holes might evaporate via Hawking radiation, leaving a thin soup of fundamental particles and energy. This would be the end as far as any organized energy or life is concerned, a quiet, cold night that never ends. It sounds melancholy, but it would be so far in the future that these words fail to convey the timescales. Add 50 zeros to a year and you're not even close. Some theoretical scenarios foresee even more dramatic finales. If dark energy isn't constant but grows stronger over time, it could lead to a big rip. In that case, the expansion would, billions of years hence, become so violent that galaxies, stars, planets, and eventually atoms themselves would be torn apart. This is considered unlikely by most scientists right now. Data hint that dark energy is constant, not increasing. But it's a dramatic possibility, the universe literally ripping itself apart. Alternatively, maybe dark energy could change sign, or gravity could one day overcome expansion, leading the universe to stop expanding and start contracting. In that hypothetical case, everything would rush back together in a big crunch, possibly ending in conditions like the Big Bang started with. Some have imagined this could even bounce and lead to another Big Bang, an oscillating or cyclic universe. Currently, evidence doesn't favor a big crunch. Our universe seems to be speeding up outward, but it's one of those ideas that shows we still have much to learn about cosmic destiny. All told, the evidence as of now points toward the quieter heat-death scenario, expanding forever, gradually cooling and dimming. If that's the case, we're fortunate to exist now, in a young, star-filled universe. New stars are still being born. Galaxies are bright. We can see the grandeur around us. In the extremely far future, the universe will be more lonely and dark. But that ultimate night is incomprehensibly far away. For now, the cosmos is bustling with light and life's potential. On more immediate scales, our own sun will change our local environment long before any of those cosmic ends. As mentioned, in about 1 billion years, the sun's increased brightness might push Earth into a runaway greenhouse, likely ending most surface life. By about 5 billion years, the sun will turn into a red giant, potentially engulfing Earth, or at least rendering it completely uninhabitable. But perhaps by then, any intelligent life descended from us, if we survive that long, will have found new homes among the stars, carrying the legacy of Earth with them. Meteor showers occur when Earth passes through the trail of debris left by a comet. Tiny sand grain or pebble-sized pieces of comet dust hit Earth's atmosphere at high speed and burn up, creating bright streaks in the sky. Shooting stars. Each year, regular meteor showers like the Perseids in August or the Leonids in November grace our skies when Earth plows through old comet paths. These showers are like nature's fireworks, softly sizzling overhead on schedule. Watching a meteor shower on a calm night, you might see dozens of little streaks per hour, each one a tiny piece of an ancient comet giving its life to put on a show for us. They're gentle reminders that Earth is moving through a dynamic environment, and even a grain of cosmic dust can create a momentary flash of beauty. We experience tiny bits of the cosmos every day. Micrometeorites, dust-sized specks from asteroids or comets, are constantly raining down on Earth. You might have cosmic dust on your rooftop or in the soil outside, tiny spheres of once molten rock that fell from the sky. Every year, it's estimated tens of thousands of tons of interplanetary dust settle onto Earth. So in a literal sense, a little piece of the stars becomes part of our world continuously. Sometimes when you see a quiet dust mote floating in a sunbeam, it could actually be a visitor from space, ending a journey that began millions of miles away. Even auroras, the northern and southern lights, are an interaction with cosmic forces. Charged particles blown from the sun, the solar wind, get funneled by Earth's magnetic field into the upper atmosphere near the poles, where they excite atoms and molecules, causing them to glow. The result, shimmering curtains of green, red, and purple light that dance in polar skies. Other planets have auroras too. Jupiter and Saturn have even more powerful ones, courtesy of their strong magnetic fields and energetic space environments. It's comforting to think, as we sleep, that Earth's magnetic field is quietly deflecting harmful solar and cosmic radiation and turning some of it into beautiful auroral night lights in far northern and southern skies. Throughout space, the interplay of forces creates light shows and gentle radiation that we seldom notice. We're cocooned by Earth's atmosphere and magnetic field, kept safe from most cosmic harshness. And within this cradle, life has flourished. Life itself is one of the universe's greatest mysteries. We know of only one instance, Earth, but the ingredients and conditions for life might exist in many places. We wonder about microbes in subsurface oceans of moons, or hardy creatures in the clouds of Venus, or forests under an alien sun. As of tonight, we haven't found clear evidence of life beyond Earth, but the search is just beginning. Perhaps, as our technology improves and as we dream bigger, we'll answer that profound question: are we alone? If the universe is teeming with life, it hasn't made itself obvious yet. It might be that space is just so vast that civilizations are isolated by distance and time, like fireflies blinking on distant hills that never notice one another. It could be that life is common, but mostly microbial, or intelligent life is exceptionally rare. Or maybe we truly are one of the first, or the only, technologically capable species in our galaxy right now. In any case, the night sky invites us to wonder without end. Human beings have sent instruments to touch the sun. NASA's Parker Solar Probe is swooping closer to the sun than any spacecraft before, actually dipping through the sun's outer atmosphere, the corona at times. It's studying the sun's magnetic field and the origin of the solar wind, seeking to understand why the corona is hotter than the sun's surface and how solar flares and eruptions work. To survive, Parker carries a thick heat shield and spends most of its orbit far from the sun, only briefly making close passes. It's a remarkable feat of engineering. We've sent a probe into the domain of a star. We have also brought back pieces of other worlds. The Stardust mission flew through a comet's tail and returned tiny dust grains to Earth. Japan's Hayabusa and Hayabusa 2 missions landed on asteroids and brought back samples of asteroid material. NASA's OSIR-ISREX mission is returning samples from asteroid Bennu. These samples are precious. They're literally bits of other places, untouched by earthly contamination, holding clues to the early solar system. It's amazing to think, while you sleep, there are bits of comet and asteroid in laboratories, being examined by scientists who are uncovering the story of how our planets formed. Among the unexpected discoveries of recent years was the presence of complex organic molecules in space. We've detected amino acids on meteorites, and even in the thin atmosphere of Saturn's moon, Enceladus, via the Cassini spacecraft's instruments. We've found interstellar clouds containing simple sugars, alcohols, and other organic compounds. Space, it turns out, is a chemical laboratory. The building blocks of life seem to form readily in the cold and dark of molecular clouds and on the surfaces of dust grains. So, when life started on Earth, it may have had a boost from ingredients delivered by comets and meteorites, pre-made in space. It's a gentle thought. The universe doesn't just provide awe and wonder, but also perhaps a starter kit for life wherever conditions allow. Even the structure of our own Milky Way galaxy isn't fully known because we're inside it. Imagine being in a forest, trying to map the entire woods. It's tricky. For a long time, we thought the Milky Way had four major spiral arms, but recent data show it might have only two prominent arms with several shorter spurs. Our galaxy also has a bar of stars in the center and an interesting peanut or hourglass shape in its central bulge, discovered through infrared observations of the star distribution. We have to infer the Milky Way's shape using observations of stars and gas around us, kind of like mapping a city by lampposts seen through fog. Bit by bit, we are getting a clearer picture, but it's a reminder. Even our home galaxy holds secrets. When you gaze at the Milky Way band on a clear night, you're looking through a thin plane of that galaxy, unable to see its full form. A bit like standing inside a giant work of art, too close to see the whole. Thorne-Zhitkov objects were once purely theoretical, part star remnant. Imagine a red supergiant star with a neutron star core inside it. It could happen if a neutron star, maybe from a supernova, gets engulfed by a giant star. Such an object would look like an unusual star with strange chemical signatures. Only one candidate in the small Magellanic Cloud has been identified that might fit this description. It's a reminder that nature's variety may include even more exotic states of matter and stellar configurations than we've catalogued. The universe allows experiments far beyond what we can create on Earth. Our Milky Way is part of a small cluster of galaxies called the Local Group. This includes Andromeda, the Milky Way, the Triangulum Galaxy, and dozens of dwarf galaxies. The Local Group itself is part of a larger structure called the Virgo supercluster, which in turn is part of an even larger Laniakea supercluster. It's hierarchy upon hierarchy. When we map these clusters, we see that galaxies tend to form long filaments and sheets with voids in between. It's like the large-scale universe has a texture. Our galaxy is streaming toward the Virgo cluster, the heart of our supercluster, which in turn is influenced by the great attractor we spoke of. It's a big dance, and everything is interconnected by gravity. One of the most profound images in astronomy is the Hubble Ultra Deep Field. To create it, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky for an extended period, over 11 days of total exposure time. What emerged was an image of thousands of galaxies scattered across that once blank spot. Every smudge of light in the picture was an entire galaxy. Some are among the farthest and oldest seen. It's like holding a grain of sand at arm's length and seeing it filled with a cosmic city of galaxies. When you consider that every point in the sky, if observed deeply enough, would reveal galaxies upon galaxies, it really underscores how huge and populated the universe is. Yet, from our perspective here, the night looks mostly dark, punctuated by stars of our own galaxy. Sometimes gravity itself provides us a telescope. A massive cluster of galaxies between us and a distant object can act as a gravitational lens, bending and magnifying the light from the background object. We've observed this multiple times. Distant galaxies or quasars appear smeared, stretched into arcs, or even duplicated into multiple images around a foreground cluster. It's like nature's magnifying glass, allowing us to see objects that would otherwise be too faint or small. One famous example is Einstein's cross, where a distant quasar's light is lensed by a galaxy into four distinct points of light around the galaxy's image. Gravitational lensing not only produces pretty patterns, but also tells us about the mass, including dark matter, in the lensing object. It's a clever cosmic trick. Mass curves space, and light follows the curves. Gravitational lensing also lets us map the invisible dark matter in clusters by seeing how it distorts background galaxies. In some spectacular cluster collisions, like the Bullet Cluster, astronomers observed that the majority of mass, as inferred from lensing, was separated from most of the normal gas, as seen in X-rays. This is considered evidence that dark matter exists and doesn't collide with other matter like gas does. The gas from two colliding clusters slowed down and got left behind, while the dark matter and galaxies, which are mostly empty space, passed through. It's comforting in a way. Even though dark matter is invisible, the universe has ways for us to sense it indirectly by the gentle warping of distant light. Our Milky Way's central black hole is relatively quiet now, but in billions of years, when it eventually merges with Andromeda's black hole, a supermassive black hole binary will form. Such pairs emit gravitational waves as they spiral inward. We haven't observed a supermassive binary merge yet. They take a long time. But astronomers are using pulsar timing arrays, monitoring signals from many pulsars, to search for the telltale low-frequency gravitational wave background from many supermassive binaries across the universe. Someday, we might detect the hum of galaxies merging by hearing their black holes in spiral. When high-energy cosmic rays, extremely fast particles from space, hit our atmosphere, they create showers of secondary particles. We've even detected a few cosmic rays of astonishing energy, far beyond what we can produce in accelerators. They likely come from outside our galaxy, perhaps from events like neutron star collisions or active black holes in distant galaxies. Some of these ultra-high energy cosmic rays remain a bit of a mystery regarding their exact origins. It's as if nature has particle accelerators far more powerful than anything we've built, flinging atomic nuclei across intergalactic space. On calm nights, one wouldn't know it. But occasionally a proton or iron nucleus from a galaxy billions of light-years away slams into the upper air above us, a silent messenger of some cataclysmic process out there. There's a peculiar cosmic phenomenon called fast radio bursts, FRBS. These are extremely brief, millisecond flashes of radio waves that come from far outside our galaxy. They were discovered in the past decade or two. Most FRBs just happen once, and we haven't pinpointed many of their sources. A few repeat, though, allowing us to identify their host galaxies, often dwarf galaxies or magnetars, highly magnetic neutron stars, as likely sources. FRBS can emit more energy in a millisecond than the Sun does in days. What exactly causes the non-repeating FRBS is still a topic of research. It could be flare stars, merging stars, or something exotic like collapsing pulsars. They are one of the newest cosmic mysteries. The sky, when monitored with fast radio detectors, occasionally lights up with these powerful yet fleeting flashes, and we're still figuring out why. Even within our Milky Way, we encounter puzzles. In the 2000s, astronomers found unusual radio sources near the galactic center that flared on and off, dubbed the galactic center radio transients. At least one source, nicknamed the cosmic burper informally, defied easy explanation for a while. It wasn't a known type of pulsar or flare star. Later studies suggest some may be a type of slow pulsar or magnetar, but they taught us that our own galaxy can still surprise us with new classes of objects. Toward the center of our galaxy, there are also hypervelocity stars, stars moving so fast that they're escaping the Milky Way's gravitational pull. How do they get such speed? We think many are produced by interactions with the central black hole. Imagine a binary star system, two stars orbiting each other, wandering near the black hole. The intense gravity can capture one star, or shred it, and fling the other outward at tremendous velocity like a slingshot. These exiled stars race through the halo on trajectories that will eventually take them into intergalactic space. It's a bit sad and romantic, a star forever leaving its home galaxy, doomed to roam alone between the galaxies. But the night sky it sees would be incredible, the whole Milky Way shrinking behind it, and the solitude of cosmic night ahead. The cosmos has its quiet places too. Voids, huge regions of space with very few galaxies, span hundreds of millions of light years. One of the largest known voids is the Buta's void, sometimes called the Great Nothing, which is roughly 330 million light years in diameter. yet contains only a handful of galaxies. If you found yourself in the center of that void, you would hardly see any galaxies in the sky. You'd be in a true cosmic emptiness, aside from the occasional galaxy far off in the distance. It's hard to fathom such emptiness when our night sky, from our vantage, seems full of stars. But stars are in galaxies, and galaxies cluster, and between those clusters lie these vast, dark expanses. The existence of giant voids is another facet of the cosmic web, dense here, empty there. Back to Earth for a moment, think about atoms. All the atoms around you and in you are mostly empty space. If the nucleus of an atom were a golf ball, the electrons would be like tiny peas orbiting a few kilometers away, and everything in between would be empty. If you could squeeze out all that empty space, you could fit all humanity's atoms into a volume smaller than a sugar cube. It's wild. We feel solid. The bed you lie on feels solid, but that solidity is an illusion created by electromagnetic forces. At an atomic level, there's vast emptiness inside matter. In a poetic sense, maybe that's why we resonate with the cosmos. We carry within us tiny voids as vast proportionally as the spacing of stars. Light itself has a finite speed, as mentioned, which means when we communicate with spacecraft at other planets, there's always a lag. It's a reminder that even within our solar system, distance introduces silence and delay. At the speed of light, it takes a little over a second for a signal to go between Earth and the Moon, about 3 minutes one way between Earth and Mars at closest, and over an hour to reach the edge of the solar system. The idea of quick conversations across the stars is, sadly, unrealistic. If we ever detect a signal from, say, a civilization 100 light-years away, a round-trip exchange of hello and hi would span centuries. The universe's vastness enforces a kind of quiet isolation between far-flung islands of life, if they exist, and perhaps that's partly why we haven't heard anything. The cosmic gulf is just too great. The cosmic perspective often gives a sense of how special Earth is. So far, Earth is the only place we know that teems with life. Forests breathing, oceans teeming, creatures thinking and feeling. We have not yet found another living world among the exoplanets, though we've just started looking. Earth orbits in the Sun's Goldilocks zone, has abundant water, a stable rotation axis, helped by our Moon, and just the right balance of elements to nurture life over billions of years. From a spaceship's view, Earth shines as a delicate blue and white orb, a pale blue dot, as Carl Sagan famously called it, hanging in the cosmic dark. Astronauts often experience the overview effect upon seeing Earth from orbit or the Moon, a profound sense of our planet's fragility and the unity of the people and life on it. National boundaries vanish, conflicts seem petty. They see one world, borderless, bathed in sunlight and alive with color against black space. It instills a deep urge to protect that world and cherish it. Even while we marvel at the universe's wonders, the cosmic perspective gently reminds us that our home is unique and precious, deserving of our care and love. Ancient humans looked at the night sky and saw patterns, constellations, and wove stories about them. Those same stars, shifting slowly over millennia due to Earth's precession but largely the same, are above us tonight. The myths and figures varied. Orion to the Greeks was a hunter, to the Egyptians it was Osiris. In Chinese lore, part of Orion was a great warrior, or perhaps a collective of different stories. The stars have been a canvas for human imagination across all cultures. It's comforting to think that as you lie here, you share that experience with countless dreamers before you over tens of thousands of years, all looking up at essentially the same sky, wondering, storytelling, and finding meaning. Many bright stars have their own names, often Arabic in origin, passed down from medieval astronomers. For example, Betelgeuse, the reddish star in Orion's shoulder, comes from a phrase meaning the armpit of the giant. Aldebaran means the follower, because it chases the Pleiades cluster across the sky. Sirius means scorching for its brightness. When you whisper the names of stars, you're speaking words used by sky watchers centuries ago. It's like a quiet connection across time and space. Lying in bed under an imaginary sky, you can trace your own constellations in your mind, connecting stars like dots and creating figures, a calming, almost meditative practice. The universe, for all its vastness and complexity, operates under a set of natural laws that appear to be the same everywhere we look. The fusion in distant stars follows the same physics as in our sun. The spectrum of a galaxy, a billion light-years away, obeys the same atomic rules as light on Earth. This consistency, the cosmic order, is what lets us understand the universe at all. It's quite elegant that from simplicity, like gravity, electromagnetism, nuclear forces, such diverse and complex phenomena emerge. Swirling galaxies, blossoming nebulae, living planets. In some ways, the universe is like a calm, predictable clock. In others, it's endlessly creative. And we, tiny as we are, have managed to decode many of its workings, which is a testament to the power of curious, rested minds. As you listen to these cosmic wonders, consider that every moment Earth is moving through a new part of space, orbiting the sun, which orbits the galaxy, which moves in the universe. We never come back to exactly the same spot. Each year, Earth travels almost 1 billion kilometers around the sun. Each orbit is a new path through space we've not taken before. In a sense, even if you stay in one place your whole life, you're always traveling, riding the Earth on its grand journey. If you imagine compressing the entire 13.8 billion year history of the universe into one calendar year, the Big Bang happens at the stroke of midnight on January 1st. Our Milky Way forms perhaps around mid-March on this timeline. The Sun and Earth form around early September. Life on Earth appears in late September. Complex life, multicellular organisms emerge around mid-December. Dinosaurs roam on December 25th, Christmas Day, and go extinct on December 30th. Modern humans appear at 11:52 p.m. on December 31st, and all of recorded history fits in the last few seconds before New Year's midnight. We are extremely young compared to the universe, yet here we are with minds capable of contemplating all of time and existence, however briefly, before we drift into a gentle sleep. Through the eons, the universe has transitioned through phases. In the early radiation era, light and energy dominated. Then matter took over, allowing stars and galaxies to form. We live in what's called the stelliferous era, the time of stars. Far in the future will come the degenerate era of cooled remnants, then perhaps a black hole era, and eventually a dark era when hardly anything emits light. But those poetic terms describe a future so distant it almost merges with eternity. For now, starlight is abundant, and the cosmos is rich with activity. We're lucky to witness the cosmos in its starry, luminous age. Hearing all these wonders, you might marvel at how much we've learned. Just a century ago, we didn't even know there were other galaxies besides the Milky Way. We thought the universe was just our galaxy. Now we see the universe is vast and expanding. We've unraveled starlight to know what stars are made of. We've sent probes across the solar system. We've detected gravitational whispers from collisions, black holes billions of light years away. It's quite an accomplishment, yet it's also just the beginning. We're only a few centuries into systematic science, and only a few decades into the space age. In time, if we remain curious and compassionate, who knows what more we'll discover or become. Throughout human history, we've built an incredible body of knowledge about the world and cosmos around us. And yet, we're only at the beginning of this journey. The universe, a twilight realm of enigmatic secrets, remains replete with unexplained mysteries and paradoxes shaped by unseen forces. It's often said the universe is like a giant jigsaw puzzle made of infinite pieces, but we can only see a small portion of it and guess at the rest. In the vastness of the cosmos, many more secrets await our curious minds. There are still countless wonders yet to be discovered, enticing us to keep exploring, learning, and dreaming. Now the stars in your mind's sky begin to fade gently behind your closing eyes. We have drifted through 200 cosmic wonders tonight, from swirling galaxies to whispered particles, from the birth of stars to the far destiny of the universe. We've journeyed from the small, atoms, dust, and the seeds of life, to the immense, galaxy clusters and cosmic horizons, and from the familiar, our moon and sun, to the exotically unfamiliar neutron stars and quasars. Through it all, we found ourselves connected to the cosmos in surprising ways. You wandered through stellar nurseries, danced along spiral arms, and gazed toward the galactic center glowing behind veils of dust. You flew in your thoughts to distant exoplanets and imagined their skies. You pondered what might lie in a black hole's darkness or in the silence between galaxies. You felt the subtle tug of gravity weaving the tapestry of the cosmos, and the gentle light of ancient stars falling softly upon us. Somewhere in that vastness, somehow, we find ourselves, a small planet among many, circling a quiet star, floating through a story too wide for our eyes to see all at once. Yet we are a part of it. The iron in your blood was forged in a star's core long ago. The calcium in your bones was created in a supernova. The oxygen you breathe was cooked in stellar furnaces and blown into space to later form our planet's air. The atoms of your body trace their lineage to the beginnings of time, born from the same matter that now fuels stars and swirls in nebulae. We are children of the universe. Tonight, as you rest, the cosmos continues its grand dance. Stars are being born in nurseries far away. Other stars are dying in brilliant flashes. Planets are whirling around countless suns. Galaxies are colliding in slow motion. And space itself is stretching quietly, carrying galaxies ever further apart. It all unfolds on scales of time and size that are hard to imagine, but it's comforting to know that even as you sleep, the universe hums along, vast, ancient, but also calm and steady from our perspective. We, tucked in our small corner, are safe to dream about it. As you sink deeper into sleep, feel that you are floating gently in the spiral arm of a galaxy, a tiny warm speck in a quiet sea of stars. The universe around you is dark, but not empty. It's filled with the lullaby of distant starlight and the soft murmur of atoms and particles that once were part of shining suns. You are cradled by creation. Gravity holds you gently to Earth. Earth carries you around the sun carries you through the galaxy, and the galaxy dances through the cosmos. If you happen to still be awake at this moment, you can let go now. It's okay to release any remaining thoughts and let yourself drift off. You're part of a vast and beautiful universe, and it will watch over you as you sleep. There's no need to worry or even to think. The stars will continue to shine, and the earth will continue to turn. You can simply be here and now, cozy and safe, floating on the gentle current of the cosmos. Thank you for joining this journey tonight. I hope you sleep well and dream softly beneath the quiet stars. Good night.